General chemistry students. In this video, I am going to go over the Unit 2 review guide on atomic structure and nuclear chemistry. Alright, so the first one that we worked on was the model of an atom and developing that model and what it looks like. And what we discovered is if we took the nucleus and we increased the size of the nucleus to something larger, say like a tennis ball, the entire atom would be huge, like the size of Grimes, or larger than the size of Grimes, like very, very large. And so if we put this into perspective and we look at what's in this little tiny spot being the protons and the neutrons, and those things being everything that has mass, and then in the electron cloud, we have the electron, which have no mass, are super, super tiny, then we can see that the atom as a whole object is going to be mostly empty space. You know, if we have the nucleus here and the electron cloud is up here, we have everything that has mass right here, this tiny electron somewhere in this area here, so most of it is just going to be empty. All right, the next one here is the Dalton's law of atomic theory. Now, there's 4 different parts of this, and I'm not going to go over each individual part, but do make sure that you review those for the test. What I want to focus on here, though, is the parts of Dalton's law that were wrong. Now, it's important to note that even though there were 2 parts that were wrong, or that have recently been, not recently, have since been disproved, Dalton's law of atomic theory laid the framework for everything that we know about the atom today, and so it still is very, very important. But we want to point out those things that have changed since he came up with this this atomic theory, this idea of what an atom is. One is that atoms cannot be created, destroyed, or subdivided. Now, this one is wrong, or this one has been proven different because it can be subdivided into protons, neutrons, and electrons. Now, what's still correct about this is that if you subdivide it into these things, it's no longer an atom. It's the subatomic particles, and these subatomic particles can then be broken down into things even smaller than that we don't study. The other one is that all atoms of a single element are identical. Now this one is wrong, because not all atoms of a single element are identical, because we have isotopes. So if we take hydrogen, has 1 proton, another hydrogen has a proton, another hydrogen has a proton. This one has no neutrons, so it has a mass of 1. This one has 1 neutron, so it has a mass of 2. This one has 2 neutrons, it has a mass of 3. All of these different atoms, atom 1, atom 2, atom 3 here, are all hydrogen. But they're different isotopes of each other. And they're not identical because they have different masses, different number of neutrons, different masses. All right, let's go on here. Objective 3, we're looking at the different parts of the atom. The 2 main areas, so you got to be careful with this one because you're like 2, but I thought there were 3. You're thinking of the subatomic particles. We're looking at the areas here, and the areas are going to be the nucleus and the electron cloud. Now, I'm going to do it like this because I think the next question is going to ask me about the different parts of this stuff. The different subatomic particles, which we can then kind of put up into this diagram here. So the nucleus has the protons, and the neutrons. And then has a positive charge, this has a negative charge. Protons have a mass of 1. Let's see here, mass equal 1, and so do neutrons. Now the role of these, the protons, the role is the identity of the atom, and the neutrons is going to be the isotope. So if we change the number of protons, we get a different atom. If we change the number of neutrons, we get a different isotope. Now for the electrons, electrons have a negative charge. Their mass is negligible, meaning they have almost no mass, and they are responsible for the charge. So we have where each is located, protons and neutrons in the nucleus, the charge. Protons are positive, neutrons are neutral, electrons are negative. Mass, the protons, the neutrons are the things that have mass. Electrons do not. They have a mass of 0 when we compare it to the mass of these things. And the role, identity is the protons, the isotope is the neutrons, and the charge is going to be the electron cloud. All right. We have the ion questions. An ion is, oops, that's really terrible. Erase. An ion is an atom or group of atoms. We'll talk more about that in future chemistry parts, but an atom with a charge. That's it. The two types of atoms, we have cations. These have a positive charge. We have anions. These have a negative charge. Cations are formed by the loss of electrons. The anions are formed by the gain of electrons. So cations, if we have sodium, now sodium has the atomic number of 11, so it has 11 protons. If it's neutral, it has 11 electrons. Notice there's no charge here. No charge listed means that it's neutral. But if we have sodium with a positive 1 charge, it is going to have 11 protons and 10 electrons. So we have one more positive thing than we do negative thing. So it's a positive 1 charge. Now conversely, if we had oxygen, 8 protons, because its atomic number is 8. I find that information on the periodic table. No charge, so they're the same. Now if we did oxygen here with a negative 2 charge, we would have 8 protons and 10 electrons. Notice that we have 2 more electrons here than we do have protons, so it becomes a negative 2. Okay. Distinguish between a mass number and average atomic mass. We are going to have isotopes involved here. So the mass number is the protons plus the neutrons, because those are the subatomic particles that have mass. And that is the mass number, oops, that is of a specific isotope. Remember we talked about the hydrogen examples before, where the average atomic mass is the average of all of the isotopes put together. So that's the main difference. This takes into account all of the isotopes. This one only takes account one isotope. Right. All right, so we have a table here that we're going to use in order to fill out the numbers. We've practiced lots of these so far, and we'll do this one quickly and get the answers. Alright, sorry for the brief delay there. I had to get a periodic table. Let's see here. We have the atomic number of protons. We have silver. Silver has a positive 1 charge. So the number of protons is going to be 47. I get that from the periodic table. And the number of protons then is also 47. Now, I know that the atomic number of protons are always the same. So I'm just going to go ahead and fill this into the table, 6 and 6. And the atomic number, remember, is coming from the periodic table. Then I'm going to go through and finish out silver so we can see how everything is done. The number of neutrons, remember the protons plus the neutrons gets the mass number. So I have 108 minus 47, that is going to be, I believe, 61 neutrons. The number of electrons, if the charge is neutral, so no charge here, the protons and electrons equal each other. But since we have a positive 1 charge, we're going to have 1 more proton than we do electrons. Remember that the protons can't be changed, only the electrons. The nuclear symbol looks like this. Silver is Ag. The mass number goes on the top, and the number of protons, or the atomic number, goes down in the lower left-hand corner. Charge, upper right-hand corner. 35 is going to be bromine. And notice up here it says element and charge, so we're going to have to come back to that maybe to see if bromine needs a charge. We have 35 protons, 35 for the atomic number, so those are the same. Neutrons, 35 plus 45 gets us 80. That's that number, and then we have 36 electrons. We have 1 more electron than we do protons, therefore this is going to be a negative 1 charge. Symbol, bromine, negative 1. 80 for the mass number, and 35 for the atomic number. Carbon, 6. Now, notice that there is no charge listed here. That means that we can assume that it does not have a charge if electrons aren't given, so we're going to say 6 electrons as well, because the protons and electrons have to equal to each other if there's no charge. Protons plus neutrons gives us the mass number, so it is carbon 14, 6, and no charge. All right. Here we have a nuclear symbol, and this is then asking us to go the other direction. So we went from the information here to make the nuclear symbol. Now we're going to take the nuclear symbol and go the other direction. So this is oxygen. Protons is 8. Neutrons is 8. I got this because this is the atomic number, so this has to be the protons. This is the mass number. And the protons plus neutrons have to equal the mass number. Electrons is 10. I have 2 more electrons to get the negative 2 charge. So we have 8 protons, and 10 electrons gets us a negative 2 charge. Okay. Isotopes. Isotopes is something we already talked about, but let's review again. Isotopes are the same element, but the atoms have different masses. And so we looked at hydrogen, so let's look at that again. We have hydrogen, 1 proton, hydrogen, 1 proton, hydrogen, 1 proton, always hydrogen. Mass number of 1, mass number of 2, mass number of 3. So we have different number of neutrons. So we can tell if they're isotopes of each other if they have the same number of protons, but a different mass. And that equals an isotope. All right. This is the calculation portion of it. We're looking at how to calculate the average atomic mass. And remember that in order to calculate average atomic mass, we need to have what's called that percent abundance. If we look at like lithium, lithium on the periodic table has an average atomic mass of 6.941. has two different isotopes, lithium-6 and lithium-7. Oops. Notice that the mass of lithium here is much closer to the lithium-7. That tells us that there has to be much more of the lithium-7, like 98% of this element is going to be the atom made up of lithium-7, and then a small portion is going to be those lithium-6 atoms. Because if we had equal quantities of each of these, the average would be 6.5, right in between. But since it's not, we know that it has to have more lithium-7. All right, let's practice an example here of magnesium. Magnesium has three different isotopes, and it has the percent abundances listed here. Remember that if we do calculations with percents, we have to turn them into a decimal. Now, in order to get the average atomic mass, which is what this problem is asking for, we're going to take the mass and multiply it by the percent abundance. The same for the others. We're going to add up all those numbers. That will get us 24.305. And notice that is the same average atomic mass in the periodic table, which is also the answer here that it gives us. Now, it gives us the answer here because we know what we're after. We know what element is on the periodic table. We can just go to the periodic table and look up the average atomic mass. What we want to do is make sure that we understand how to calculate that. And so we have to show our work to get credit for a problem like that. All right, we're going to look at nuclear fission and nuclear fusion, and then the other radioactive decay problems. We have fission, which is one large atom splitting to form two smaller ones, and then nuclear fusion is the opposite, two small atoms to form one large. Some examples. Well, we've done a lot of examples here. We have uranium and 92, and that goes through the nuclear fission process to produce two different atoms plus the neutrons. Now, the two different atoms here, I can't remember what they are. I think they're krypton and barium. Let's play with that and see if it works out. We have 36, and barium is 56. Yep, that works. That makes 95. And then we have the two different mass numbers. And the mass here for krypton is going to be, let me do something here real quick. Yeah, I'm not going to be able to figure out these here without looking it up. Maybe have a notebook here. Hold on, yeah. Just 2 seconds. Krypton 92 and barium 141. Sorry for that delay. Now, if we add up these two numbers, we don't get 235. But if we add up all three numbers, we do get 235. 92 plus 141 plus 3 ones gets us that 235. So everything on the left-hand side has to add up to everything on the right-hand side. The nuclear fusion example is going to be our hydrogen. We have a hydrogen with one neutron, and we add that to another one. And then we can put those together to get a helium atom plus another neutron. So there's the neutron. Now this neutron doesn't do anything for us, however these neutrons do. These neutrons then can start a chain reaction, which is going to be the next problem, but let's talk about it right now. Oh, I forgot about this part, one neutron. So in order for that uranium to start the process, it has to have that neutron. You probably noticed that when I was doing that something was missing, and there it is. So that one neutron is what starts this process. Now if we require a neutron to start the process and the process produces neutrons, then those neutrons are going to be able to start new processes with other uranium atoms. Right here. And then this one can also go through the process, and then more and more and more until that turns into a chain reaction, and this thing just continues to go until we run out of uranium atoms. All right. Fusion reactions are found in the sun. Fission reactions are found in nuclear power plants. Both are used in nuclear weapons, but we aren't going to accept answers related to nuclear weapons for questions like this on the test. All right, we have the last part here, which is alpha, beta, gamma radiation. These are the nuclear decay problems. We have then all of this, and actually I'm not going to go over this right here because we have an additional worksheet, additional sheet in class that we did with all of this, and so I want you to refer to that instead of the review guide. If you want to rewrite your stuff here for some extra studying, that would be fantastic, but primarily we're going to go ahead and just use that review sheet or that extra worksheet on this stuff as the example. Now what we can do is these three problems down here and practice these. So we have carbon-14 here going through beta decay. I know it's beta decay because it has that electron symbol. And we have 14,7 nitrogen as our answer, so that is our question mark. Remember that in beta decay, a neutron turns into a proton and gets rid of an electron to maintain the charge. So the electron is that beta particle, and we get that nitrogen atom in the end. 24195 americium is what this is, this Am, and it produces an alpha particle, so this is alpha. Here, we'll do this as beta, this is alpha. So we are left with, see, 23893, no, 237. 237, and that gets us neptunium. NP is our answer there. And here we have the nitrogen turning into oxygen. Notice that we're increasing the atomic number by 1. That means that we're going to eject a beta particle. So this is beta decay. Notice that I used this is for beta and this for beta. It doesn't matter, but you should know that both. Also, this is going to be our alpha symbol, so you should know that one too. All right, guys. Good luck on the test when it comes. If you have additional questions, make sure that you are signing up for AO.